You've zipped something today. Maybe a jacket. Maybe jeans you've owned for years. That motion took half a second. What you didn't notice: two rows of teeth interlocking at exactly the right angle, held together by geometry so precise that pulling them apart by hand is nearly impossible. 7 billion of these mechanisms roll off factory lines every single year. Until one breaks, you'll never think about why the others don't. In 1893, inventor Whitcomb Judson unveiled his masterpiece at the Chicago World's Fair, the clasp locker, a revolutionary fastener that would eliminate buttons forever. Crowds gathered around the demonstration. Investors watched closely. The device jammed immediately. Clasps popped open under the slightest pressure. Metal hooks caught fabric and refused to release. Judson spent years perfecting drawings that looked brilliant on paper. The mechanism simply didn't work in the physical world. He died in 1909, still trying to fix it. The company he founded hired a young Swedish engineer named Gideon Sundback to solve what Judson couldn't. When Sundback's wife died in 1911, he buried his grief in the workshop. 14-hour days, hundreds of prototypes. By 1913, he finally cracked the code. Judson's original design used 4 clasps per inch. They couldn't distribute pressure evenly. Any strain on the fabric caused the whole thing to burst open. Sundback's breakthrough was density. He increased the count to 10 teeth per inch, more than double. Each tooth became smaller, more precisely shaped. The math changed everything. With more contact points, each individual tooth bore less stress. But density alone wasn't enough. Sundback redesigned the teeth themselves. Cups on the underside, nibs on the upper surface. When 2 rows met, each cup nested perfectly onto the opposing nib. Metal embracing metal at exactly the angle required. The fit had to be precise to fractions of a millimeter. Any variance and the teeth would grind, jam, or refuse to mesh entirely. The real genius hides inside the slider. That small metal housing you grip contains a Y-shaped channel invisible from outside. As the slider moves upward, the 2 fabric strips enter from below at an angle. The channel's walls press inward, forcing teeth toward each other. At the narrowest point of the Y, each tooth has no choice but to interlock with its opposite. The geometry is self-correcting. Even if teeth approach slightly misaligned, the channel guides them into proper position. Downward motion reverses the process. The Y widens gradually. Teeth separate in sequence, 1 pair at a time. This controlled release prevents random disengagement. Tug sideways on a closed zipper with surprising force. The interlocked teeth distribute that stress across dozens of contact points. So if the mechanism is this simple, why did it take 20 years of failure before someone got it right? Every tooth must be identical, not similar. Identical. Modern manufacturing requires tolerances of plus or minus 0.05 millimeters, half the thickness of a human hair. Sundback didn't just design the zipper. He invented the machine to make it. His SL machine fed Y-shaped wire through dies, punching and crimping each tooth directly onto fabric tape. Today's machines stamp 2,000 teeth per minute. A single millimeter of error compounds across millions of products. Quality isn't about inspection. It's about eliminating the possibility of imperfection at the source. One Japanese company understood this better than anyone else on Earth. YKK produces half of all zippers made globally. 7 billion units every single year. Enough zipper tape to wrap around the planet 50 times over. But here's what separates them from every single competitor. They manufacture everything in-house. They smelt their own brass, spin their own polyester thread, weave and dye their own fabric tape, forge their own teeth, cast their own sliders, even fabricate the cardboard boxes for shipping. When you control every variable, you eliminate every excuse for failure. A $200 pair of designer pants uses a 32-cent YKK zipper. The math seems absurd until you realize one failed zipper makes an entire garment completely unwearable. Here's what most people miss. The slider contains a tiny spring mechanism that maintains constant pressure on the teeth. Too little tension, and the zipper slides open on its own. Too much, and the pull becomes exhausting. Engineers calibrate this pressure to specific applications. Heavy outdoor gear requires different tolerances than delicate dress zippers. Each product category has its own testing protocols, its own acceptable ranges for pull force, lateral strength, and cycle durability. The zipper you're wearing likely traveled through multiple countries before reaching you. Brass refined in one, fabric woven in another, assembly completed somewhere else. Yet despite this complexity, failure rates hover below 0.5%. 14 zippers per American per year. That's the average consumption rate. Jeans, jackets, bags, tents, sleeping bags, boots. We interact with this mechanism more often than almost any other fastener in daily existence. Yet it remains essentially unchanged since 1913. Buttons require careful alignment. Velcro wears out and loses grip over time. Snaps pop unexpectedly under strain. The zipper solved a problem so completely that a century of innovation hasn't improved on the core design. Sundback's interlocking teeth still mesh the same way they did back then. The Y-channel slider still guides them together. The engineering was right from the very beginning. Next time you zip something closed, you'll feel it differently. That smooth resistance isn't friction, it's geometry. Dozens of precisely machined teeth finding their partners in sequence, faster than you can perceive. A mechanism so reliable you forgot it existed. So simple that explaining it takes longer than using it. Those 3 letters stamped on the pull tab aren't decoration. They're a promise that every single tooth will find its match. So when's the last time you actually looked at what's holding your jacket together?